Hello everybody and welcome to this research seminar on the Port Askaig Formation of the Garvellic Islands and Islay in western Scotland. Here are some excellent exposures of this relatively undeformed Neoproterozoic glacial succession. My name is David Webster. I am the meeting secretary of the Glasgow Geological Society, and the Society is honoured to be hosting this event on behalf of the Cryogenian Subcommission. There are 4 sessions in this program, 2 today and 2 tomorrow, with a live Q&A at the end of each session. All the presentations were pre-recorded, so this video was compiled from the respective recordings and the live Q&A sessions added at the end. Sessions 1 and 2 have only a recorded audio track, whereas sessions 3 and 4 have a video track with the audio. This meeting is an online version of the 2-day conference originally planned for spring 2020 in St Andrews. One of its aims was to share ideas and field questions from other experts in the field as part of a major collaborative effort to produce a new Geological Society of London memoir on the Port Askaig Formation. The team also want to update the ICS subcommission on the Cryogenian Stratigraphy on the wealth of new data and interpretations that have arisen in recent years. The subcommission has 21 voting members, including Ian Fairchild from Birmingham University in England, who is one of the research team members. Ian's been the driving force behind getting this meeting organised and set up, so many thanks to him. So we're going to move on to the first session. The first bit is a short introduction to the islands with some drone footage shot by Jordan Mertes and narrated by Doug Benn. This is followed by Tony Spencer's talk on the context and the research history, Ian Fairchild on the pre-glacial geology, and then Roger Anderton on the stratigraphic architecture.
The Garbelachs, a splendidly isolated group of islands off the beautiful west coast of Scotland, and without doubt one of the world's great geological marvels. For the past few years, Tony Spencer has brought together an international team of geologists to study the Port Askaig Formation on the Garvellach Islands, the rocks that he studied as a PhD student half a century ago. Using the island's only building as a base, we have been able to access the rocks again and again with ample support from local boatmen Alistair McLaughlin and the Lady Gale. The Port Askaig Formation on the Garvellach Islands includes a 600-metre section of Neoproterozoic glacial strata, miraculously preserved within the highly deformed metamorphic rocks of the Caledonian orogenic belt. And the wild and exposed coastline means that the rocks are often perfectly clean for study. Now, our ability to study these rocks has been enhanced by the skills of drone pilot and data analyst Jordan Mertes. And flying the drone, we've been able to conduct systematic surveys of the exposure throughout the islands, from here on Dunconnell in the east of the Shane through to Holy Island in the far west, allowing us to gain access to cliffs and exposures that until now have been strictly for the birds. This wild and rocky cove on Holy Island is very, very difficult to reach on the ground, involving exposed scrambling along the steep coastline. But using the drone perched happily on the hilltop, we were able to survey these rocks in great detail, taking systems of photographs backwards and forwards, looking at the rocks from every angle. Now, using structure from motion technology, these photo surveys can be turned into 3-dimensional models of the exposure. First of all, turning the photo survey into a sparse point cloud. The next stage of analysis, turning that into a dense point cloud, which in turn is used to generate a high-resolution mesh describing the 3-dimensional geometry onto which the photographs are projected. The end result being a highly detailed 3-dimensional rock of the exposure, which we can study from the comfort of our own desks. And these models, as you can see, exhibit huge amounts of detail that are impossible to view from anywhere on the ground. And now the final stage of the process, where views of the three-dimensional model are used as the basis of accurate planimetric logs of the sections. And these have been produced for many of the sections now, and this is still very much a work in progress. And finally, a fly-through of some of our favourite places. This is the Northwest Cove on Garbelak, a very, very remote spot, and it took us several visits to record this, involving the loss of one drone. And here, the bedding plane on the surface of D22 on Holy Island, with its well-known network of polygonal sand wedges, here shown in false colour on the left, highlighting the true colour image shown on the right. And last but not least, the spectacular gorge of Bialach and Tarabert, which exposes some of the most iconic sections in the Port Askaig Formation, the disrupted beds. These exposures are very, very difficult to reach, and hitherto have been very, very difficult to study until now.
My name is Anthony Spencer, and I want to welcome you to this series of 13 presentations reviewing our work on the Port Askaig Formation. In this first lecture, I will give a short introduction to the formation, 7 slides, and its interpretation, 10 slides. Then I will briefly show the history of research on the formation and explain the plan of this meeting. The Port Askaig Formation is one formation in the Dalradian supergroup. It occurs in about 25 separate outcrops from Western Ireland to northeast Scotland. The area where it is best seen is in southwest Scotland, in Argyll, in the area outlined in red here. The Dalradian supergroup is approximately 25 kilometres thick, and the Port Askaig Formation occurs in the middle. It is one formation amongst a total of about 40 formations and groups which make up the Dalradian supergroup. The radiometric age dates of these rocks are few. At the base, an episode of metamorphism is dated at about 800 million years. Towards the top, lavas have given a date of about 600 million years. There have been many investigations of the chemostratigraphy of the Dalradian strata. The recognition of the Garvellic Anomaly supports the identification of the Port Askaig Formation as Sturtian. Ian Fairchild will tell you more about that in Lecture 2, and Roger Anderton will tell you more about the position of the Port Askaig Formation in the Dalradian in Lecture 3. The Port Askaig Formation is fully developed on the island of Islay around Port Askaig. There it is underlain by the Losset Limestone Formation and overlain by the Bonahaven Dolomite and Jura Quartzite formations. The Port Askaig Formation is best seen in the chain of islands called the Garbellachs, here outlined in red. In our 12 presentations, most of the illustrations will be from there. Here are simplified lithostratigraphic columns below, within, and above the Port Askaig Formation. The formation itself contains 5 members, each with a different character. The diamectites have been numbered from diamectite 1 at the base of the formation to diamectite 47 near the top. The diamectites change from dolomitic in member 1 to arenaceous in member 4. Dolomite beds occur in members 1 and 2, whilst white sandstones are dominant in members 3 and 5. These upward changes in the lithologies of the strata in the formation are accompanied by related, gradual, upward changes in the clasts present. Dolomite and limestone clasts, which we call intrabasinal, are dominant in diamectites in member 1. Quartzite and granitic clasts, which we term extrabasinal, are dominant in members 3 to 5. Ian Fairchild will tell you about the Garbelak Formation in Lecture 2. At the end of the meeting, Doug Benn and Bruce Lavelle will tell you about the environmental changes in members 1 and 2 in Lecture 11, and I will tell you about the environmental changes in members 3 to 5 in Lecture 12. The Garvellic Islands are a wonderful place to do geology, especially when the sun shines. This is a view looking west along the chain of the islands. The strata dip to the south at 35 degrees. There is a raised rock platform with continuous bare rock exposures. Because of the dip and the coastal outcrops, the islands expose 670 meters of strata with no gaps. This is a very simplified geological map of the islands and the surrounding sea floor. There are 4 main islands, 10 small islands marked with red arrows, and 5 rocks exposed at low tide. The base of the Port Askaig Formation is exposed on the north of Garbellach and Dunconnell. Members 1 and 2 are exposed, 1, 2 and 3 are exposed along the chain of the islands. We think that members 4 and 5 form the seabed ridges south of the islands, but they're not exposed above sea level. Boat travel is essential. This is our boatman, Alistair McLaughlin. He takes us out to the islands and between the islands in the big boat, and then we land in the rubber dinghy. Now I want to show you some photographs of the Port Askaig Formation. Here is a massive, unstratified diamectite with granitic boulders. It is number 38 in our numbering system. Most of the diamectites look like this. They are homogeneous and lack any stratification. In terms of their origin, these massive diamectites could be glacial or may have arrived as mass flows. Therefore, we have searched for features which allow the depositional mechanism to be distinguished. I will show you a few of these distinctive features, but you will see many more in lectures 4 to 12. Here is one of the features distinctive of a grounded ice sheet, a glaciotectonic fold. The tiny figure outlined in yellow is Rosemary Dartnell. She gives you the scale. The folded rocks are dolomites and dolomitic siltstones. The fold is inside a huge block, the outer edge of which is marked by the green line. This block measures 200 meters in length, 40 meters in thickness, and at least 60 meters in the dip direction. It is contained within diamectite 13, whose base and top are shown by the red lines. We call this bed the Great Breccia. Note that the axial plane of the fold is steeper than the dip of diamectite 13. The ice was moving towards the northwest. This is the second type of feature I want to show you, which is evidence of grounded ice. It is a boulder pavement composed of granitic boulders at the base of diamectite 33. It was formed by the ice sheet moving across the surface of the underlying preglacial sandstone. We think that most of the diamectites were deposited from grounded ice. but at a few stratigraphic levels there is evidence of floating ice, such as this dropstone. You will hear about many more glacial geology features in Lecture 4 by Doug Benn, Mike Hambry and Jordan Mertes. Here is one of the features allowing us to infer periglacial conditions. You're looking down on the top surface of diamectite 22. It is covered by a network of sandstone wedges arranged in polygons. These wedges formed as subaerial permafrost contraction cracks filled with windblown sand. Here are examples of another feature allowing us to infer periglacial conditions. These are frost-shattered stones formed by freezing and thawing under subaerial conditions. Here is the third type of feature allowing us to infer periglacial conditions. These are cryoturbation folds formed by freezing in winter and thawing in summer. You will hear much more about all of these periglacial features in Lecture 5 by Richard Waller and Mike Hambry. This view shows a 50-meter thick section in which 6 climatically related episodes are recorded. Diamectites 33 to 35 were deposited by grounded ice. On their top is a subaerial periglacial horizon with sandstone wedges and frost-shattered stones. Next is a marine sandstone with large tidal crossbeds. Then the ice sheet advanced again to deposit diamectite 36. On its top surface is another subaerial periglacial horizon, and that in turn is overlain by a marine tidal sandstone. Based on the types of distinctive features that I have shown you in the last 7 slides, we can interpret the climatically related episodes in the formation as shown in this table. Here are the 5 members with their thicknesses and the numbered diamectite beds. In the 1,100 meter thickness of the Port Askaig Formation, with its 47 numbered diamectite beds, we currently recognize 28 glacial, 25 periglacial, and 23 non-glacial episodes. I now want to go on to the third topic in this lecture, the history of research on the formation. This slide gives a brief overview of that history. The special character of the formation, that it contains granite boulders scattered through a sandy mudstone, was recognized 200 years ago by James McCulloch, who was one of the early pioneers in Scottish geology. 50 years later, James Thomson suggested it recorded glacial conditions. The modern phase of the study of the boulder bed was started in 1961, when Wally Pitcher and Robert Shackleton measured the succession in the Garbellachs and numbered the 38 diamectite beds there. This led on to my PhD studies, in which I proposed there had been 17 glacial advances and meltings. In 1983 to 2006, Nicholas and Caroline Isles and Emmanuel Arnold studied the Garvellic outcrops and advocated that many of the diamectites had arrived as mass flows. Doug Benn and Tony Brave returned to a glacial origin in 2006. Then, in the last 10 years, a team of geologists has again studied the Port Askaig Formation. Now you will see 2 slides giving more information on the topics coloured in yellow. This is the published abstract in which Thomson proposed a glacial origin. The most important sentences are underlined in red. The ages of these rocks was not then known. Now we know that this was the first cryogenian diamectite to be proposed as glacial in origin. Here is a list of some of the important new findings we have made during our fieldwork in the last 10 years. Each of the lecturers you will hear today and tomorrow, and numerous others, have brought their different expertise to the work and so made many new findings. Our aim is to publish a new memoir on the Port Askaig Formation. Now I want to briefly explain the structure we have chosen for this conference. This is the programme. There are 12 separate presentations. In the next slide, I will show you how these 12 presentations relate to the stratigraphy and interpretation of the Port Askaig Formation. Here I have used the table of climatically related episodes to show how the lectures cover the stratigraphy and the subject matter. Lecture 2 by Ian Fairchild will describe the carbonate formations beneath the Port Askaig Formation. Lecture 3 by Roger Anderton will explain the stratigraphic setting of the formation. Then lectures 4 to 9 will cover particular topics. Lecture 4 by Doug Benn, Mike Hambry and Jordan Mertes will explain the features used to interpret the glacial strata. Lecture 5 by Richard Waller and Mike Hambry will cover the periglacial features. Lecture 6 by Dilshad Ali will show how we can analyse the individual events preserved in one of the periglacial horizons. Lectures 7, 8 and 9 will cover the non-glacial strata. Ian Fairchild on the origins of the Dolomites, Roger Anderton on the marine environments, and Bruce Lavelle on the continental environments. Then there will be a virtual field trip to Scale Lethacuan by Bruce Lavelle. There, 75 metres of strata expose many glacial and periglacial features and continental environments. The final session will explain the environmental changes. In Lecture 11, Doug Benn and Bruce Lavelle will cover members 1 and 2. And in Lecture 12, Anthony Spencer, that's me, will cover members 3 to 5. In the last period, we will discuss some selected topics responsible for making the Port Askaig Formation an extraordinary record of cryogenian glaciation. Thank you.
It is a pleasure and a privilege to speak to you today about some wonderful geology that I've been fortunate to re-engage with over the last decade or so. Much of it because of Tony Spencer's drive and initiative, and many people have contributed to the material I will present. I will describe what rocks we see on the ground and some aspects of their geochemistry, and put this knowledge in a global stratigraphic framework. To keep non-experts on board, I will introduce some basic concepts of correlation, so please be patient, members of the Cryogenian Subcommission. By the end, I hope that all of you will be able to see why these exposures are of global interest. Internationally, the Port Askaig rocks are correlated with the Sturtian panglaciation, a sharply defined climatic event 55 million years long, a first-order perturbation in climate in Earth's history. A possible scenario for the onset of glaciation is rifting of the equatorial supercontinent Rodinia. leading to drawdown of atmospheric carbon dioxide by weathering, but we still have much to learn. The Cryogenian period encompasses the older Sturtian and the younger Marinoan panglaciations. It is grounded in rocks, the Cryogenian system, but geologists have yet to make a formal definition on the ground. Here, on the Garvellic Islands, is a possible place to make that definition. You are looking at a composite drone image of the coastal rock platform of the main island, Garvellach, looking down the dip of 70 metres of carbonate beds that are overlain by the Cryogenian Port Askaig Formation. The blue dashed line is a lithostratigraphic boundary reflecting the local deposition of sediment, and which in this case lies within a transitional change from a non-glacial to a glacial regime. For intercontinental correlation, we need a chronostratigraphic boundary. And in 2018, we proposed that a level within the carbonates corresponding to that purple dashed line be defined as the base of the Cryogenian. An outstanding area of international cooperation between geologists is the geological timescale, which assembles the most informative sections worldwide to define named periods of time, systems of rock, and likewise epochs and series, ages and stages. This is chronostratigraphy. Separately, geochronologists make the best estimates of the age of these divisions in millions of years. This is chronology. Each geological division is defined at its base by what is formally known as a GSSP, a global stratotype section and point. This is a specific location with well-known attributes that allow other locations with simultaneously formed rocks to be correlated with it. Colloquially, GSSPs are known as golden spikes, after the famous ceremony when railroads in the USA from the east and the west met in the middle. The iron spike holding down the rail was symbolically replaced by a golden one. As you can see, many GSSPs have been defined, but some are missing. And so far, only one has been defined in the Precambrian. The youngest system and period in the Precambrian is the Ediacaran. I was a member of the international working group that defined its base in 2004 at the section seen in the photograph on the left in the Flinders Ranges in South Australia, near the base of a carbonate cap to the Marinoan glacial deposits. Although younger GSSPs are mostly defined on the basis of fossils, that is, by biostratigraphy, here the global correlation depends on the carbon isotope composition of the marine dolomite cap. This is an example of chemostratigraphy. The photo on the right shows the equivalent aged rocks in Svalbard and illustrates the change from glaciogenic deposits to the non-glaciogenic yellow cap dolomite, part of a major transgression. This is recognizable worldwide and reflects climatostratigraphy, the end of a global ice age. At the time the Ediacaran definition was made, there was only one reliable radiometric determination of its age, so it was a bold decision. However, as you can see in the data tabulated on the left, we now have evidence on 4 continents of synchroneity of the Marinoan cap carbonate at 635 million years. For the start of the Sturtian glaciation, there is close agreement between observations on 3 paleocontinents, as you can see in the lower left, between 717 and 716 million years. Currently, the base of the Cryogenian is defined at 720 million years, pending identification of a GSSP. In 2016, the Subcommission on Neoproterozoic Stratigraphy agreed how this should be approached. And as you can see in the red type, the idea is that it will be defined beneath the oldest unambiguously glaciogenic deposits, and that precise correlation would require high resolution carbon and strontium isotope data. The Tonian, Cryogenian and Ediacaran systems collectively make up the Neoproterozoic era. Isotopes of several elements have proved of value in the Neoproterozoic, but the two most widely used are carbon and strontium. The delta 13C value represents the ratio of the rare element 13 carbon to the common isotope 12 carbon, scaled to a marine fossil standard. On this scale, organic matter is 25 to 30 parts per thousand more negative, that is depleted in carbon-13, than seawater or carbonate minerals formed from it. The Neoproterozoic era displays mainly positive delta 13C values in marine carbonates, as you can see in the upper part of the diagram, with time periods with distinct negative anomalies. Originally, all these anomalies were linked to glaciation, perhaps by lowered biological productivity, making the inorganic carbon-13, carbon-12 ratio smaller. However, some are clearly distant to glaciation, whilst those preceding glaciation are now known to have terminated before the Ice Age. A negative carbon-13 signature is also characteristic of the cap carbonates, but the signal is subtly different in the Sturtian cap and the Marinoan cap. The Sturtian cap starts negative and rises. The Marinoan becomes more negative upwards. So carbon isotopes are clearly valuable for fine-scale stratigraphy, but for the big picture, strontium isotopes are the most powerful tool. Here we're looking at the ratio of strontium-87 to strontium-86. Strontium-86 is stable, whereas strontium-87 is radiogenic, that is, it is created by radioactive decay of rubidium-87, which substitutes for potassium and is found in continental granitic rocks, for example. So continental growth during the Neoproterozoic has led to a large secular rise in the ratio of strontium-87 to strontium-86, as you can see in the lower part of the main panel. The exception to that is the period between 750 and 720 million years, which you see enlarged in the lowest panel, which demonstrates a falling trend just before the Sturtian glaciation. The lower panel includes the latest results from Ethiopia by Park et al., who suggest the fall may be due to arc-continent collision and enhanced weathering of young volcanic rocks. But the key point for us is that the Sturtian glaciation is preceded by carbonates with strontium isotope ratios of less than 0.707. Now let's see how this applies to the Port Askaig Formation. First, we have to explain that the lower Port Askaig Formation contact is different in its two key locations. On the map on the right, you can see the large Isle of Islay, and in the far north of the map, the Garvellic Islands. The diagram in the centre shows that the Port Askaig Formation rests on the Garvellic Formation in the Garbellachs, but on the Losset Formation on the Isle of Islay. This photograph from the Losset area on Islay shows that the Port Askaig Formation overlies a terrestrial unconformity on a periglaciated surface of the Losset Formation. The right-hand photos show the equivalent surface on the Garbelaks, and this surface is present at the top of diamictite 13, the Great Breccia of Spencer 1971. The Lossip Formation of Islay is therefore older than the Garvellic Formation. And here is the chemostratigraphy of the carbonate rocks underneath the PAF to back that up. The formation names are given on the right, whilst on the left in red you see indicated what is seen on the Garbelachs and what is seen on Islay. This diagram plots stratigraphic height vertically against carbon isotopes horizontally on the left and strontium isotopes horizontally on the right. Looking at the Islay rocks, which are in the lower part of the diagram, on Islay there are positive carbon isotope values which decrease upwards. For strontium isotopes, we look for the minimum values because these are least altered. On the right, we see that the minimum strontium isotope value is around 0.7066 on Islay. On the Garvellachs, higher in the diagram, the minimum strontium isotope composition is slightly lower, at 0.7064. Whilst in the upper left of the diagram, you can see a distinct negative carbon isotope anomaly, the Garvellic Anomaly, which terminates just below the Port Askaig Formation. Clearly then, this chemostratigraphy points to the Sturtian age of the Port Askaig Formation. Since there has been some discussion in the literature about a possible younger age for the Port Askaig Formation, here are some additional pointers to its Sturtian affinity. I've listed 6 pieces of evidence in total. We've just looked at the low strontium isotope values of less than 0.707 in the underlying carbonates. Secondly, there is the presence of iron formation. The centre photograph shows us magnetite, mineralized dolomite breccia that's found on Islay. And this can be compared with a typical Sturtian iron formation, the Hollowilena ironstone from South Australia. We don't see these ironstones in Marinoan glacial deposits. A third characteristic is that of marine interbeds in between the diamictites, the glacial diamictites. And a spectacular example of that is shown in the lower photograph with thick sets of cross-bedding in quartz arenites between diamictites in member 3. Fourthly, the great thickness of the formation as a whole. It's over 1 kilometre in thickness, representing the subsidence during the long duration of the glaciation, the Sturtian glaciation. The fifth point is that there is a capped dolomite with a distinctive carbon isotope composition. This is not yet in the literature, but in the dolomite talk tomorrow, I will show you the evidence that we do indeed have a capped dolomite associated with the Port Askaig Formation, and that its carbon isotope composition is the same as of that of Sturtian caps worldwide. The sixth piece of evidence arises from the work of Tony Prave and colleagues, who show that there is a representative of the Marinoan glaciation much higher in the Dalradian stratigraphy. And there's a very nice carbonate on that, which is found in Ireland, and it's very, very scrappily developed in Scotland. Now, we've established that the Garvellach section is key in this discussion. So let's examine the Garvellach formation in more detail. This slide shows an overview of the 70 metres of succession that is exposed. The central graph shows us the carbon isotope composition from the base to the top of that section. Carbon isotopes are around -5 parts per thousand for the first 50 metres, then they rise to above 0 below the Port Askaig Formation. We have called this the Garvellic Anomaly, replacing the previous term Islay Anomaly, as these strata do not occur on Islay. There is a mixture of limestone coloured blue and dolomite coloured orange in the lower half of the section, but only dolomite in the upper part, where there is also more evidence of subaerial exposure. Here are some examples of lithologies from the lower half of the Garvellic Formation. Carbonate mudstones dominate, with some horizons with small stromatolite bioherms, as in the upper left photograph, and local flake breccias, as in the lower right photograph. Siltier lithologies are more likely to have been dolomitized, and such layers can show wave ripples, as shown on the lower left, and grading, as in the lower right. Enigmatic polygonal cracks, shown in the upper right photograph, have a dolomite fill and appear to be subaqueous. Next, I show the interval between 38 and 60 metres in the Garvellic Formation, and the corresponding bed numbers are shown in red on the log at the left. First, we see an interval of dolomitic siltstones, which includes the first subaerial exposure surface, which is illustrated in the lower right photograph with intraclass. In bed 27 is a compacted wedge-like structure that is interpreted as silicified anhydrite in a desiccation crack. In beds 28 to 38, there are several horizons of gypsum crystal pseudomorphs, shown by the black biconvex lozenges next to the log. The silica contains anhydrite inclusions, although in the case of the biconvex crystals, these were originally gypsum. From bed 28 upwards, the base lithology is dolomite with distinct sandy horizons. These are broadly tidal flat facies. Bed 39 is a slightly paler weathering dolomite, that is less Faroan than the beds above and below, and it's overlain by a dolomitic siltstone, which is bed 40. As you can see from the carbon isotope plot in the upper left, this is where the crossover from negative to positive carbon isotope values occurs, and so is the proposed position of the GSSP between the Tonian and the Cryogenian. The first signs of ice are ice-rafted horizons, which are shown by the green ellipses on the log. These ice-rafted horizons are dominated by coarse sand to granule-sized grains. Bed 46A is the first occurrence, and they then become abundant in bed 48A, close underneath the Port Askaig Formation. Also, in this upper part of the Garvellic Formation, there are wave reworked sandstones. This includes a marker bed, which is bed 42, which has long wavelength wave ripples, which are very useful for fine-scale correlation. They're even found in a raft of the boundary beds found within the megabreccia diamictite 13, the Great Breccia, on the island of Argyll in the Garvellic group. The photograph at the lower right shows us this wave-rippled bed 42. Another possible indicator of ice is this brecciated surface of a dolomite horizon in bed 48A. It looks to be more disrupted than you'd expect from desiccation, and therefore could indicate freezing processes and the formation of ice brecciating the dolomite. The photographs here are from an horizon very close to the base of the Port Askaig Formation, within this Argyll raft that I mentioned just now. It's remarkable because it shows no signs of tectonic deformation, and very fine silt particles are readily visible, which in the metamorphic Daradian is quite unusual. So it seems that this material was protected from deformation within the megabreccia diamictite 13. So we see here lamination of finer and coarser material, as well as distinct dropped sand grains. And there is a pellet of siltstone that has been deposited, which is enlarged in the lower right photograph. The field appearance is shown on the lower left. It's quite distinctive. We also see syndepositional faulting, as shown by the yellow arrow in the upper photograph, which is something else that's characteristic of ice-rafted deposits. The diamictites in the Port Askaig Formation are numbered. So D1 is the basal diamictite, which we see on Dunconnell, the smallest islands of the Garbelak group, and on Garbellic Island itself. Diamictite 1 is interpreted as subglacially deposited. It has a sharp, locally erosional base and is up to 10 meters in thickness, but it also disappears laterally. This photograph is taken from within diamictite 1 on Garbelak, and it shows a recumbently folded sediment clast, illustrating subglacial deformation. In his talk, Doug Benn will illustrate a range of examples of subglacial deformation in the Port Askaig Formation. The base of the Port Askaig Formation shows significant lateral variability. We can have confidence in this stratigraphic framework because of the consistent presence of a marker rippled bed, 42, which is close to the base of the three right-hand logs shown here. Diamictite 1, as seen in the left-hand two logs, disappears laterally to be replaced by ice rafting horizons in the right-hand two logs. Above the D1 level, in the right-hand two logs, there are further occurrences of gypsum pseudomorphs in dolomitic tidal flat bashes, identical to those in the Garvellic Formation. So a particularly evocative discovery was of these stellate pseudomorphs, which grow into the top surface of diamictite 1. Hence, the initial glacial advance did not destroy the existing tidal flat setting, nor its capacity to precipitate dolomite and gypsum. So, in the top surface of D1 and in the non-glacial deposits between diamictites 1 and 2, we see these gypsum pseudomorphs silicified, preserved there. However, above D2, the interbeds between diamictites have a different character. They become fluvial sandstones and lacustrine laminites. Deposition continues of alternating diamictites and continental deposits through to the thick grounded ice deposit D13, referred to as the Great Breccia in Spencer's 1971 memoir. Hence, subsidence in the Garvellachs area was able to keep pace with eustatic sea level fall, allowing a continuity of deposition between marine and non-marine environments in an arid climatic setting. The Garvellach section has much in its favour as a candidate GSSP, despite the lack of paleontological or radiometric constraints. It can be accessed within a couple of hours from the mainland, but it won't be visited casually. The exposure is continuous, and the weathering state on the raised shore platform allows structures to be seen clearly. There is a clear chemostratigraphic context with high-quality strontium isotope data from underlying limestones and a well-constrained carbon isotope anomaly. In addition, evidence for ice rafting is within a few meters above the candidate GSSP, shortly followed by evidence of a glacier advance. Nevertheless, the precursor conditions of dolomitic tidal flats with large gypsum crystals were re-established, making this a remarkable example of an environmental transition to glaciation. The Garvellic Formation is not connected continuously by exposure downwards to older marine sediments such as those seen on Islay, but this is where drilling onshore or on the surrounding seabed could make this connection. And this was established by reconnaissance work by the British Geological Survey, reported in the paper by Fairchild et al. In Precambrian Research in 2018. The Cryogenian Subcommission made a group visit to Islay and the Garbelachs in 2013. This was early days in our work, and we had not yet established the true transitional nature of the base of the Port Askaig Formation. Since 2013, progress in investigating candidate GSSPs by the Subcommission has been difficult because of the remoteness of many sections and the almost universal unconformity at the base of Sturgeon glacial units. A special issue of Precambrian Research in 2018 was devoted to issues related to the Subcommission's work. A new phase has recently been started with an accelerated programme to identify a GSSP within the next 3 years. Many people have been involved in generating the data summarised here, as can be judged by this authorship list of our 2018 paper. Since the paper went to press, Niamh Rhys Doherty has written an undergraduate master's dissertation on the boundary sections. I first visited this section in 1979 with Maurice Tucker, and later Tony Spencer and I harmonised that log with one of his from the 1960s. We're also grateful for Tony Prave's inspired carbon isotope synthesis of the Daradian in 2007, which has provided much inspiration. Thank you.
I'm going to talk briefly about the stratigraphic and structural context of the Port Askaig Formation in Argyll. Starting here with figure 1 from Tony Spencer's original 1971 memoir, the black dots show the location of the Port Askaig Formation across Scotland and Ireland, and the hashed area is the outcrop of the Dalradian supergroup. The Argyll area lies in the centre of this outcrop belt. Throughout this area, throughout the whole of Scotland and Ireland, a distance of about 700 kilometres, the stratigraphy of the Port Askaig Formation is similar. There's a progressive evolution from diamictites bearing dolomite and limestone clasts and with a dolomitic matrix, upwards into diamictites with predominantly quartzite and granite clasts and a more quartzitic arenaceous matrix. Likewise, the interbeds between the diamictites change from predominantly dolomites and dolomite cemented sandstones upwards into quartz cemented quartzitic sandstones. These changes can be seen throughout the outcrop, and in the central area from Donegal to Argyll, it's possible to divide the formation up into 5 individual members on the basis of these characteristics. So these individual members can be traced considerable distances. Individual beds obviously can only be traced short distances. They could certainly be followed the length of the Garvellic Islands, 6 kilometres or so, but it's difficult to trace individual beds for longer distances than that. This shows the general stratigraphy, the 5 members of the Port Askaig Formation shown in the middle here, roughly 200 metres thick each, overlying the units on the left, which are the carbonate rocks of the Losset Formation and the Garbelak Formation. The Port Askaig Formation is in turn overlain by the Bonhaven Dolomite on the right, a clastic and dolomite sequence. And then finally we have the Jura quartzite, a very thick quartzite,
unit, which I shall return to later. So what's the bigger picture of the Port Askaig Formation? Where was it deposited? Well, this is a reconstruction from about the beginning of the Sturtian, 720 million years ago, about the beginning of the Port Askaig Formation, and it shows the Rhodinian supercontinent with the area of the Port Askaig indicated by the red star here. You can imagine that there was a seaway extending from the open ocean in through the area marked by the star in towards the more interior parts of the supercontinent. This is the picture at 720, and if we roll it forward a little while, 680 million years, which would be late in Port Askaig times or possibly after, you can see that the Rhodinian supercontinent is well and truly breaking up into individual continental blocks. If we move further forward to about 600 million years, it's broken up altogether, and the areas to the north and south of the red star here become the Baltic continent to the south and the Laurentian continent to the north, with the Iapetus Ocean between them. So this is a picture that I drew nearly 40 years ago to try and envisage what it would have been like in the Dalradian area during deposition. And I think we have to imagine deposition in a series of fault-bounded blocks, because the crust would have been undergoing fairly extreme extension and thinning. So all the way through the Dalradian, the crust is being stretched to produce the subsidence, and eventually the stretching and thinning becomes so extreme that, as we see in the bottom picture, the crust thins so much that we get extensive basaltic volcanism. And we see this in the Tavialic volcanic rocks, which are about 10 kilometres above the Port Askaig Formation in Argyll. Eventually, of course, the crust breaks through altogether, and we get the development of the Iapetus Ocean. And after all this extension and thinning, of course, eventually in the Ordovician there was a period of compression. The Caledonian orogeny squashed this great pile of sediments, and we can see here on Peter Thomas's lovely perspective view looking across the Grampian Highlands, very tight vertical folds and horizontal naps. This reminds us that the Dalradian has suffered a lot of compression, tectonic compression. The area we're interested in is where the red star is, bottom left corner, in the relatively less deformed parts of the central bit of the Dalradian. Turning now to the stratigraphy, this is a stratigraphic column for the whole Dalradian, an immensely thick pile of sediments, often taken as 20 to 25 kilometres thick, although this is the thickness that you arrive at by adding together the formations measured at their thickest points. The real thickness at any one point would probably be no more than half that. The Port Askaig Formation, roughly in the middle here. The right-hand side shows a schematic curve of water depth, not particularly well defined below the Port Askaig Formation, but above you can see there are two very pronounced shifts to the right, which indicate very rapid basin deepening, presumably a consequence of very major crustal extension and faulting. You get a general picture that the extension, the subsidence, the faulting got more severe as we go up through the Dalradian. This is a map of Argyll, and the areas of interest include the Garvellic Islands here, Port Askaig area around the east coast of Islay, the type section obviously. There are also outcrops on the Mullavar and at Benderloch, but here they're very much thinner. I also draw your attention to the large yellow formation to the south of the Garbellachs, which is the Jura quartzite that we've already mentioned, which extends from Jura onto the island of Islay. This is a lovely seabed image produced by John Howe and his colleagues at the Scottish Association of Marine Science. The black blobs in the middle are the main islands of the Garvellach chain, and the coloured areas are submarine water depths, pink being fairly shallow and blue very deep down to 250 metres or so. So you can see that the Garvellachs lie on a ridge, and that there are a whole series of ridges running parallel to it. So it looks like a fairly simple structural pattern. You can also see that immediately south of the Garvellachs on the pink area, there are little ridges here. These are probably outcrops of individual diamictites or groups of diamictites, and these can be followed on the seabed imagery. If we pull back a bit, we can see that the Garvellachs lie on an extensive ridge. Let me highlight the Garvellachs to make it a bit clearer. So you can see the individual diamictites to the south of the Garvellachs on the ridge, and they extend right off the picture. So we've got an outcrop length there, submarine, that is, of 15 kilometres or so. There is a lot of old red sandstone in this picture, so to simplify the story, let's just get rid of that. That lies unconformably above the Dalradian, and when we remove that, you can see that the structural picture looks very simple. It looks like there's a whole series of parallel to subparallel ridges. The dip is to the southeast, fairly uniformly round about 30 degrees, so we would expect to see a progressive upward stratigraphic sequence from northwest to southeast. So that, we think, is the outcrop of the Port Askaig Formation on the Garvellachs and the adjacent ridge, and it probably also extends to the north as well, where there is only one skerry poking up above sea level. And in this area, it's structurally, the seabed imagery shows that it's structurally rather more complicated. It looks very simple on the Garvellachs, but much more complicated to the north. So the stratigraphy, we can easily visualize it if we just spin the geological around. So the formations below the Port Askaig Formation are seen here at the bottom of the picture, and we're just looking more or less at a stratigraphic profile here if we take this sort of down dip view with the beds getting younger towards the top of the picture. There are some small faults between the islands, very clear on the seabed imagery. And when we saw these, we had to consider whether they might be syndepositional faults. The reason being that you can see these faults don't really affect the beds above or below the Port Askaig Formation. And they have a fairly unusual orientation for compressive faults or even extensional faults that we see post-Dalradian times. But when you look at a stratigraphic cross-section, this is Tony Spencer's lovely cross-section showing the stratigraphy of the islands, but reconstructed as a sort of down-dip view. There isn't a very obvious difference between the islands that might indicate there were major faults, syndepositional faults between them. The stratigraphy seems to ride across fairly straightforwardly. And if we look in more detail, for example, these are a couple of diagrams from Dill Shadali's thesis. It doesn't matter what the colours are, they're facies groups, but they show that there aren't major changes going across this picture. So these are a series of stratigraphic columns on the Garvellic Islands from east on the left to west on the right. And the vertical exaggeration here is extreme. It's about times 80. And this is from member 1 and another one from member 2. Again, there seems to be a lot of stratigraphic continuity. It's complex, it's stratigraphically complicated, but there's no reason to infer major structure control here. So these faults probably aren't syndepositional. What they are is possibly related to a much bigger fault system to the east, which is important. These are syndepositional faults that affected the Dalradian after Port Askaig times, and they truncate the overlying Jura quartzite in a fairly dramatic way. And these faults are responsible for the chopping up of the Jura quartzite and the downfaulting to the right-hand side of this picture of a major basin after Jura quartzite times, in which what's called the Easdale slates were deposited. So it's these are post Port Askaig syndepositional faults, very major faults with throws of many kilometres. Now, one other interesting thing to note here is that the stratigraphy, the structure of the Port Askaig on the Garbellachs, is relatively simple where it lies next to the Jura quartzite. But when we go to the north of this, to the north of where it says inch fault, the Dalradian there is very intensely deformed. The reason being probably because the Jura quartzite isn't there to buttress it. The Jura quartzite has a huge sort of dampening effect on the compressional deformation in this area, and is one of the reasons why the outcrops on the Garvellachs are so wonderful. Right, moving quickly on to Islay. Here we can see the Port Askaig Formation around Port Askaig in that sort of a greyish colour. There are three little blobs there. This is structurally in a much more complex area. It's in the hinge of the Islay anticline. A lot of structural compression here, clearly. But the other thing I want to draw your attention to is the Jura quartzite overlying the Port Askaig Formation. It's about 5 kilometres thick in eastern Islay and stretching across onto Jura. But you'll notice if you follow that yellow area southwest, it gets a lot thinner. And by the time we get to the Mullavoe, the Jura quartzite is only about 1.5 kilometres thick. Interestingly enough, that's where the Port Askaig Formation is also very thin. So what might be happening here? This looks a bit odd because the formations on either side of the Jura quartzite seem to be congruent to the top and bottom of the Jura quartzite, notwithstanding this huge variation in thickness. Well, the likely reason for this is that we're looking at deposition across the edge of a major basin, and we're looking at syndepositional faults causing the Jura quartzite to be let down to form a thick basin to the east, but much thinner to the west. So we might imagine in this kind of area there's a fault zone during Jura quartzite times. So to envisage this a bit better, let's just whiz the map round the down dip view again. So let's put our possible fault zone in, and let's get rid of the stratigraphy and structure that's across the fold axis, which is not relevant. So you can see what might be happening here. There may well be a basin edge fault system during Jura quartzite times, as that would account for this huge change in thickness. Now, from my point of view, interestingly, of course, that seems to run right through the Port Askaig area where the Port Askaig Formation is exposed. So does this mean that there is a possibility, say these faults originated in pre-Jura quartzite times, that they may have affected the deposition of the Port Askaig Formation in the Port Askaig area? So this is the Port Askaig area, and you can immediately see it's horrendously complicated. The blue stuff are the carbonate formations underlying the Port Askaig, and the Port Askaig is the brown, the grey, the yellow and the more grey on the right. There are a lot of faults. It's very complex. There are tight faults. Clearly, a lot of this is compressional tectonics, but the important question is this compressional tectonics taking advantage of syndepositional faults and reactivating syndepositional faults that were already there and were affecting deposition at an early time, maybe as early as Port Askaig times? The Port Askaig Formation occurs in sort of 3 outcrop belts, one here, another one to the north, and another one to the west. So let me try and tie these things together into what may have been happening. So this is a very simple cartoon stretching from southwest to northeast across Islay and up to the Garbelachs and beyond, to show what I think may have been happening at the beginning of Easdale Slate times, when there was this big basin to the northeast of Jura and Scarborough and the Garvellachs, where a big deep water basin accumulated. And the major fault, the inch fault that you can see there at the left hand side of the picture, chopping the end off the Jura quartzite. So our formations of interest in the Port Askaig Formation are here in the Garvellachs, here around Port Askaig, and our very thin Port Askaig on the Mull of Ower. If we mentally backstrip this picture to get rid of the Easdale Slate Basin and give us a picture in late Jura quartzite times, it may have looked like that. In other words, the Jura quartzite was much more extensive. And the Garbellachs is, nowhere near a basin edge. It's right in the middle of the basin. It's not affected by any sort of complicated tectonics. But maybe the Port Askaig area was. And the Mull of Ower looks as if it's, in a different basin or a different sub-basin that was subsiding much more slowly. And if we wind back again to Port Askaig times, the point I'm trying to make is that the depositional context of the Port Askaig in the Garvellachs, the Port Askaig area and the Mull of Ower area are quite different, and we should expect to see different stratigraphic complications in these three areas. So to conclude, the thickness variations that we see in the Port Askaig Formation probably reflect different subsidence histories across and between different basins or sub-basins. The Garvellachs area, the Port Askaig there was deposited in a relatively central position in a rapidly subsiding basin and well away from the influence of syndepositional faulting. However, the Port Askaig area was probably at the edge of this Garvellachs basin where fault influence was likely, so we shouldn't be surprised if we see more stratigraphic complexity in this area. The Mull of Ower, on the other hand, you could say was deposited in a separate fault block, suffered much slower subsidence and accumulated really a condensed sequence with probably a lot of gaps. And then finally, the preservation of the thick and relatively undeformed stratigraphic sequence of the Port Askaig Formation in the Garvellachs results from an unusual coincidence, I would say almost a freaky coincidence, of it being deposited in the central parts of a rapidly subsiding basin, but in a position underlying this thick mass of Jura quartzite which buttressed it and protected it from intense deformation during the subsequent tectonic compression. Thanks very much.
Well, thank you very much, Roger. That was an excellent presentation. Summarised lots of things that about Islay and the Garbellachs. So we've now heard three talks from Tony, from Ian, and from Roger. So I'm going to see what people have been putting in the chat, and we'll have a sort of chat discussion. So let's see what people have got some questions. Yeah. So Matthew has already asked a question about rhenium osmium dating can be applied to the diamictites. Does anyone answer that? Maybe Ian?
Yes, this topic was the subject of an intensive investigation by Alan Rooney, who attempted to get dates from a number of different places in the Dalradian, and was apparently successful in one, which he published in 2011, but based on some limestones beneath the Port Askaig Formation in the Ballachulish area. But this date seemed a bit odd, didn't seem to fit. And in 2014, he actually withdrew the interpretation. The question is why doesn't it fit? And I don't think there's agreement on that. And I personally feel that because it's a whole rock method, it's actually really difficult to understand how the rhenium-osmium system will behave during this metamorphism. And more generally, any whole rock method, you've just got to be a little bit more careful, and you're looking for 2 or 3 dates in the right stratigraphic order in a given place, which of course it has been very successful. And Alan himself has done a lot of super work showing good, valid rhenium-osmium dates in different parts of the world. And together with the uranium-lead dates, that's really transformed our understanding of the ages of cryogenian glaciation. But it's a difficult area in which to apply that particular technique.
Okay, hopefully that sort of gives Matthew a sort of an answer to the question. So we've got that one. I'm just looking back, and Mike Ridd has asked a question or given us a little commentary about the some rocks in Phuket that he's been looking at, which maybe look obviously a bit younger than the Port Askaig. It just wonders, Tony, maybe you've been familiar in the oil industry experience of whether we've ever looked at or compared the Port Askaig with these Southeast Asian probable diamictites. What do you think, Tony?
I think the answer is no, but it's very nice to get a question from Mike Ridd, who was briefly my boss in BP something like 40 years ago, and I've never had any contact with him since then. Yeah, so no answer, I'm afraid.
Okay. Okay, Matthew's asked something that's probably a bit more technical about the Persebus member of the formation. So it's maybe Tony could just give a little answer to Matthew about the Persebus member.
Yeah, in this series of lectures, as it says in, I think, my abstract, there's lots of things we are not telling you about simply because we don't have the time. And this is certainly one of them. Ian's idea that the Persebus complex, as we now want to call it, is a glaciotectonic complex on Islay. I resisted that for a long, long time, as he will tell you, but I am convinced. So, and you will hear more about that, but you won't hear more about it in this series of lectures. So a very interesting set of rocks on Islay, yet more details to tell you in the future.
Thank you, Tony. There have been a few technical problems with sound quality, video quality. Hopefully we've managed to solve most of them. It's not easy. As I say, we're working at the limits of our technical abilities here. We're geologists, not IT specialists, but I think do tell us if you're getting particular problems. That's good. Okay, any more questions? Anyone want to unmute themselves and ask a question?
Hi, here, Fabricio here.
Hi, Fabricio.
Okay. About Argyll's et al. Interpretations that you got, debris flows, mass flows, could we have some kind of mixed environments where you have reworking of the glacials downslope, and then you have a kind of mixed glacial mass flow environment, something like that?
Shall I try answering, Fabricio? Amongst the pieces of data we have not shown you are the cross-bedding measurements from the Garvellachs. We have 200 measurements. When we plot them on one diagram, it is a completely radial pattern. So we have really excellent evidence, that's only one of the pieces of evidence, but that's pretty powerful, that there was no paleoslope. So we do not think there have been any long or even medium distance mass flows. You will see in later talk a mass flow on scale Ediacaran. This was first identified by Roger Anderton. I was very disturbed and upset when he said that. It's a mass flow, Tony, he said. But we have now come to understand that, yes, indeed, it is a mass flow, which has flown down the slope at the front of the glacier. It hasn't flown down a paleo slope, it's flown down the slope. So mass flows, we think we can eliminate long distance, medium distance, travelled mass flows as a hypothesis.
Could I come in? This is Mike Reid.
Unmuted?
Yeah, go ahead, Mike.
Yeah, very nice to see Tony Spencer there, Roger Anderton, and a few other old friends. Going to Southeast Asia again, the one thing, there's a misprint in my little comment there. It actually, the belt of these diamictite bearing beds is probably the best part of 2,000 kilometers from southernmost Thailand right up to central Burma. And I don't think anywhere in those diamictites have any striated surfaces been found. We don't have erosional surfaces, as you might, for example, in West Australia or somewhere. But normally I would have expected some of the bigger clasts to be striated. I wonder if you've seen any striated clasts there in Scotland.
Over to you, Tony.
Okay, shall I try answering again?
Yes, please.
Mike, these are green schist facies rocks everywhere. Very occasionally you can extract the granite stones cleanly. What you cannot do is extract the dolomite stones cleanly. They are metamorphosed to the matrix. Now, if you go to East Greenland, that is not the case. There is zero metamorphism there, and the dolomite stones in the Neoproterozoic tillite in East Greenland, you can find striations in 5 minutes. So unfortunately, because of the metamorphism, we have not found any striated stones, but I think there is a perfectly good explanation for that. If you go to a quaternary till in Yorkshire, the striated stones are Carboniferous limestones and Paleozoic slates, not the granites there. So you need a relatively soft rock and you need to be able to extract it cleanly. If you can't do that, you are not going to find striated stones.
Thanks.
Thank you, Tony. Yeah. Mike, does that answer your question a bit, or do you? Yeah.
It does indeed. Yes, thanks very much for that, Tony. What other comparison can I make with the the Upper Paleozoic, probably Glaciogene? I think the balance of opinion amongst people who worked on those Southeast Asian diamictites is that the role of the glacier, and I think that Isles has come up with this idea, the role of the glaciers having been to bring vast quantities of debris down to the basin margin, from where it simply slumped into this rapidly subsiding basin under mass flow processes in a marine environment. The remarkable thing is, throughout probably thousands of meters, only a couple of probable Devonian trilobite pygidia have been found, no other fossils.
Okay, it's a very interesting. I haven't know much about that, but it's very interesting to hear the comparisons. And I think some of the Australian stuff is quite deep water with a lot of big blocks in it as well. There's some people working in Australia that have found these sort of things as well. It's very deep. I've got a question from Austin Brown in West Kilbride. Austin, he's talking about how thick might the ice sheets might have been. Maybe Tony, you can come in on that one.
It's a really good question.
I think it is, yeah.
But we've a very healthy group of people, because they're all focused on what do we have evidence to talk about. And we don't have much evidence to talk about the thickness of the ice sheets, I'm afraid. Now, then if one wished to speculate, we're not talking about ice sheets kilometres and kilometres thick, I don't think. It's hundreds of meters at the most. but we don't have any evidence.
Well, you do. You have the ice was thick enough to flow. And so how that determines how thick it was, given reasonable estimates of the surface air temperature and the accumulation rate of the ice. So the climate is probably most like the East Antarctic ice sheet, which has an average thickness above sea level of 2 kilometers. But the main thing is it has to be thick enough to flow under its own weight, because we see the clear geological evidence of that. And furthermore, there are 17 tillites which have polygonal sand wedges at their top, showing that when the ice withdrew temporarily, they were subaerially exposed to cold air. So they were not deposited at the base of a continental slope. They were deposited on the shelf. So every time the ice withdrew, they were subaerially exposed to the cold air temperature, which produced the periglacial sand wedges, which are definitely not sandstone dikes.
Yeah, the only comment I'd make is thickness. I took it that the questioner was questioning me how thick was the ice at the locality of the Garvellachs. So my answer was with respect to that. We were at the margin. We were not in the centre. We were not in central Finland.
Is Doug Benn online, David? We might like to hear from him.
I don't know. Is Doug there?
Yep. I'm here listening with interest. No, a number of very good points have been made there. As Tony said, with the number of advances and retreats, but we're obviously in a fairly ice marginal situation here. We're not looking at the center of an ice sheet, so the ice thickness much of the time was probably quite low. As regards Paul's point about the minimum ice thickness required, well, yeah, it must have been 100 meters plus at least, you know, in order to get the flow. But certainly we're not looking at kilometers thickness of ice for most of most of the rocks that are preserved. And Paul did make the very important point there about the environment of deposition. That we're not looking at a continental slope environment, but a shelfal environment and frequent terrestrial exposure, which we'll be talking about in a lot more detail in talks to come.
Thanks, Doug. Thank you. Anybody else got any more questions? Any more comments? Any more contributions? We've got about another 5 minutes of this session to run. Yeah.
Mike Ridd again, could I come in?
Yeah, sure, Mike.
Just a very quick one. In Southeast Asia again, I keep going back to this, I know, and I apologize, but there the diamictite matrix is almost invariably sandy, very often with rounded sand grains. When I saw the picture that you presented of the diamictite on the Garbellachs, it looked like mud. It compared with sandy mud in Southeast Asia, the Phuket group. Do you ever see a sandy mud matrix?
Over to you, Tony.
Yeah, Mike, the number one, diamictite 1, is a dolomitic siltstone. You go up to the number 47, then you're into something which is highly arenaceous. So we have a great variety, and there is a transition as you go upwards. So some of the uppermost diamictites are completely structureless sandstones. If you stood in front of the outcrop, you'd say it's a structureless sandstone, and it takes you 5 minutes to find a stone. So the answer is everything is possible. You and I need to talk more, I think. So if you send me an email, we can continue this conversation at length.
I'd like to do that very much, Tony.
Yeah, so I'm glad we've connected people. Well, that's good. Yes. Okay. Any more contributions? Okay. If there's no more contributions to this session, I'll draw it to a close. I'm just going to pause the meeting, pause the recording, and we're going to start again at 2 o'clock British Summer Time, which is in about 20 minutes time. So you've got time for a comfort break and a cup of tea.